Imagine, if you will, the European Space Agency launching a probe named Philae into the cosmos on March 2, 2004. Its destination? The comet known as 67P Churyumov-Gerasimenko. This mission, named Rosetta after the Rosetta Stone, had one primary goal: to land the Philae probe on the surface of Comet 67P and unveil its secrets. What made this mission so remarkable? The comet was discovered back in 1969 by Churyumov and Svetlana Gerasimenko. Since then, it had intrigued scientists due to its complex structure and unique properties. Little did they know, the Rosetta mission would provide groundbreaking discoveries that would illuminate our understanding of comets and their role in the early solar system. The European Space Agency, or ESA, had been planning this ambitious mission for years. The Rosetta spacecraft was designed to be a complex and versatile explorer, capable of navigating the vast distances between Earth and Comet 67P. To achieve this, it undertook a series of flybys, including encounters with Mars, Earth, and even asteroids. The journey to Comet 67P was long and arduous. The comet orbits the Sun in a period of approximately 645 years, traveling through space on an elliptical path that brings it closer to the Sun at times and pushes it out into the depths of space during others. One of the most fascinating aspects of Comet 67P is its size and shape. Measuring about 4 kilometers in length and 3.5 kilometers in width, it is a rather large comet compared to others. As Rosetta approached this celestial body, scientists were eager to learn more about its structure and composition. The comet rotates on its axis every 12 hours, creating a unique day-night cycle. This rotation period was crucial for understanding the comet's activity and behavior during different parts of its orbit. On November 12, 2014, the Rosetta spacecraft released the Philae probe, which descended towards Comet 67P in a thrilling and delicate maneuver. This event marked the first time that a human-made object had landed on a comet nucleus. The successful landing of Philae was a historic moment for space exploration. The data sent back by the probe provided detailed information about the composition, structure, and activity of Comet 67P. By studying this comet, scientists hope to gain insights into the early formation of our solar system and the origins of comets themselves. The Rosetta mission was a joint effort by ESA and NASA, involving scientists from multiple countries across Europe and the United States. Throughout its mission, Rosetta sent back over 100,000 images of the comet, offering an unprecedented view into its complex structure and unique properties. The mission revealed that Comet 67P is a complex body with distinct regions that exhibit different types of activity as it approaches the Sun and moves away from it. By the end of its mission, Rosetta had provided a wealth of data that has helped to unravel the mysteries of comets and their importance in our solar system's history. The journey of Rosetta mission is a testament to human ingenuity and the unyielding quest for knowledge about our universe. As you continue listening, the exploration of Comet 67P will reveal even more fascinating discoveries. So, let's delve deeper into what Rosetta uncovered about this cosmic wanderer and the profound implications it has on our understanding of the solar system. Before we begin, a small request. Most of the people listening tonight aren't subscribed. If this channel has ever helped you drift off, take a moment to subscribe. It's free, it helps this channel more than you'd think, and you can always change your mind later. And if you feel like it, leave a comment telling me where in the world you're listening from and what time it is where you are. I love reading them. One more thing before we begin. I'm also a co-founder of a sleep app, built to be the most affordable one out there. No ads, ever. Just sounds and stories made to help you sleep. It may not be released yet as this video goes up, but if you're watching a little later, it might be out by now. Just search for it. It should be easy to find. It works on iPhone, Android, and everything in between. Downloading it is the best way to support this channel. Philae's journey to the comet was designed with precision and care, equipped with instruments like spectrometers to analyze the comet's composition. The lander was meant to drill into the surface and collect samples for detailed analysis. But the landing didn't go as planned. Due to the comet's low gravity, Philae experienced a bouncy touchdown. It bounced several times across the comet's surface before finally settling in a shadowed area known as Abydos Site J. This unpredictable journey was both thrilling and challenging, pushing the boundaries of what we knew about comet landings. Despite the setbacks, Philae managed to send back valuable data for over 60 hours before its batteries ran out. Among its discoveries were detailed images of the comet's surface, revealing boulders and pits that hinted at a complex structure beneath. The MUPA's instrument measured the temperature of both the surface and subsurface layers. Philae's daring mission marked a pivotal moment in our understanding of comets and their role in the early solar system. It opened doors to further exploration, setting the stage for more profound discoveries. As we delve deeper into Rosetta's findings, it becomes clear that the mysteries of these cosmic wanderers are as vast and complex as their journeys. This historic landing laid the foundation for an unprecedented understanding of comets, drawing us closer to unraveling the secrets of our cosmic origins. After the Rosetta spacecraft's historic landing, scientists were greeted by an unexpected sight, a comet with two distinct lobes often referred to as the head and body. This unique dual-lobe structure challenged our understanding of comet formations. The larger lobe, the head, measures approximately 4 kilometers in diameter, while the smaller lobe, the body, is around 2.5 kilometers. Connecting these two lobes is a narrow neck that measures about 1 kilometer in width. This peculiar structure raises intriguing questions about the comet's formation and evolution. What makes this discovery so groundbreaking is that the dual-lobe structure was unveiled only after Rosetta's landing. Prior to this, comets were generally considered to be more uniform in shape. Imagine the surprise of scientists when they realized that the comet's structure was unlike anything previously observed. This extraordinary find pushed us to reconsider our understanding of these celestial bodies. Now, let's picture the comet in the vastness of space. Two distinct lobes, a narrow neck connecting them, and an array of terrains, all floating together as one complex entity. The discovery of this dual-lobed comet structure challenges our preconceived notions about how comets are formed and shaped over billions of years. As we continue to explore the data from Rosetta, we're drawn closer to unraveling the mysteries of our cosmic origins. The dual-lobed beauty of Comet 67P Churyumov-Gerasimenko serves as a reminder of the incredible complexity hidden within the solar system. Scientists discovered jets of water vapor and dust emanating from the comet's nucleus, propelling these particles into space. This activity is driven by sublimation, a process where ice transforms directly into gas. Think of it like a hot summer day when ice in a glass melts into water. On Comet 67P Churyumov-Gerasimenko, the sun's heat causes frozen water to evaporate directly into vapor, creating these jets. These jets are not evenly distributed. They originate from specific areas called active pits and fractures. The most prominent of these is the neck region, where the comet's two lobes connect. Imagine a vast underground reservoir of ice, slowly seeping through cracks and fissures on the surface. As the sun warms these areas, it triggers the release of gas and dust. The result is a spectacular display of comet activity jets that stretch out into space, sometimes reaching lengths of hundreds or even thousands of kilometers. These are what we see from Earth as the comet's tail. But it's not just ice driving this activity. Organic compounds, which are building blocks of life as we know it, also contribute to these jets. This makes Comet 67P Churyumov-Gerasimenko a treasure trove for understanding the origins of our solar system. These complex processes create a constantly changing surface, with cliffs eroding and new pits forming. The comet is not static. It's a dynamic body that responds to the sun's heat as it travels through its 645-year orbit around the sun. As we dive deeper into these mechanisms, we uncover the fascinating processes that make comets dynamic celestial bodies, shedding light on their role in shaping our early solar system. Prepare to explore how these discoveries piece together the broader puzzle of our cosmic origins, a journey that starts with a closer look at the building blocks of life hidden within this icy wonder. It's fascinating how the solar system was born some 4.6 billion years ago, a vast cloud of gas and dust giving rise to our celestial home. These celestial bodies are time capsules, holding clues to the formation of our solar system. This intricate design provides insight into how comets form, offering a glimpse into the early solar system. The mission also uncovered that the comet's interior is porous and contains cavities, suggesting a fragile composition formed billions of years ago. These discoveries indicate that Comet 67P Churyumov-Gerasimenko and others like it were born out of the same primordial material that created our solar system. These findings bridge gaps in our understanding of how planets like Earth were formed from this ancient material. As the Rosetta mission continues to provide data, it sheds light on the early formation of our solar system, piece by intriguing piece. Prepare for more revelations as we delve deeper into the mysteries of this icy time capsule and its profound connection to our cosmic origins. The OSIRIS camera, for instance, captured stunning high-definition images of the comet's complex terrain. With its ability to resolve features as small as a meter from a distance of hundreds of kilometers, it revealed intricate details such as cliffs, pits, and boulders that paint a vivid picture of the comet's surface. But the OSIRIS camera was not alone in its mission. Accompanying it were spectrometers like VIRTIS, the Visible and Infrared Thermal Imaging Spectrometer. This sophisticated instrument analyzed the sunlight reflected off the comet to determine its composition. The comet's nucleus is made of a combination of ice, dust, and volatile compounds. The surface of the comet is a complex mix of these materials, with the dust and ice forming a layer that covers the entire nucleus. These cavities suggest that the comet is not solid, but rather a loose agglomeration of materials held together by weak forces. The volatile compounds within the comet play a crucial role in its activity. When the comet approaches the sun, these compounds sublimate, turn directly from a solid to a gas, creating the spectacular jets of material that give comets their signature tails. As the volatile compounds are depleted, the dust and ice on the surface begin to heat up and sublimate as well, contributing to the comet's activity. By studying Comet 67P Churyumov-Gerasimenko, scientists gain insights into the building blocks that may have contributed to life on Earth. With the Rosetta orbiter continuing its path around the comet after the landing attempt, the mission team prepares for the grand finale. On September 30, 2016, the Rosetta spacecraft is deliberately crashed into the comet's surface. The controlled descent allows the spacecraft to collect valuable data on the comet's composition and structure during its final moments, providing unprecedented insights that would have been impossible otherwise. Scientists speculate that a low-speed collision with another celestial body could have resulted in the comet's dual-lobed appearance. Alternatively, rapid outgassing, the process by which volatile materials escape from the comet's surface, could also explain this unique structure. The implications of these theories are profound. If a collision is responsible for the comet's shape, it suggests that comets can undergo significant structural changes over time. Moreover, if rapid outgassing played a role, it offers insight into how comets lose material as they orbit the sun, contributing to our understanding of their evolutionary processes. Though much remains unknown about these ancient celestial bodies, each new piece of data brings us closer to unraveling their mysteries. Water ice plays a pivotal role in driving cometary activity, particularly through a process known as outgassing. As the comet approaches the Sun, water ice sublimates directly into gas, contributing to the formation of jets and plumes that shape its distinctive appearance. The distribution and quantity of water ice on Comet 67, P. Churyumov-Gerasimenko, were meticulously mapped by Rosetta's instruments. These measurements revealed a heterogeneous landscape, with water ice more abundant in the comet's shadowed regions. This uneven distribution underscores the complex interplay between solar radiation and cometary ice, hinting at a dynamic history shaped by solar heating cycles. Understanding the role of water ice on Comet 67P Churyumov-Gerasimenko is more than just a scientific curiosity. As we continue to decipher the language of comets, each new discovery brings us closer to unlocking the secrets of our cosmic neighborhood. Scientists identified a variety of organic molecules, including amino acids and nucleobases. Imagine tiny fragments of this ancient comet containing the seeds of life scattered across the young Earth. These organic compounds not only hint at the potential origin of life, but also illuminate the role of comets in shaping our cosmic neighborhood's chemical landscape. As we continue to unlock the secrets hidden within these celestial bodies, each new discovery brings us closer to understanding the early solar system and our own origins. Their organic matter whispering tales of ancient cosmic processes that set the stage for life's grand journey. And as we listen to their silent songs, we find our place in this vast and wondrous universe. But this dance is not constant. As the comet approaches its active periods, its rotation rate begins to slow, and when it reaches its peak activity, it slows even further. This slowing is not merely a quirk, it's connected to the comet's surface activity. Imagine, for a moment, the power of these forces at play. Jets of water vapor and dust erupting from the comet's south pole fractures, a sight that has left scientists awestruck. The Rosetta mission revealed something profound. These eruptions, or plumes, are not just displays of cosmic fireworks, they influence the comet's rotation. The jets act as natural thrusters, slightly altering the comet's spin rate as they vent into space. This delicate balance between surface activity and rotational dynamics is more than just an interesting quirk. It holds keys to the comet's deeper mysteries. As we delve further into these secrets, we begin to understand how a comet's early life in the solar system shaped its current behavior. And so, through the lens of Rosetta's pioneering discoveries, we come to appreciate the dance of Comet 67P Churyumov-Gerasimenko, a cosmic ballet where every movement holds a story waiting to be told. These jets are not a gentle breeze. They erupt with force, propelling tiny particles into space. They were first observed by Rosetta's OSIRIS camera. The mission discovered that these jets are driven by the comet's subsurface ice, which sublimates or turns directly into gas as it approaches the Sun. This process creates a visible plume of dust and water vapor, stretching like a tail as they are pushed away by the solar wind. The exact mechanisms behind these jets remain a topic of ongoing study, but one thing is clear: these outgassing processes play a significant role in shaping the solar system. Throughout its journey, Rosetta observed how these jets change over time, ejecting material that becomes part of the coma, the fuzzy envelope surrounding the nucleus. This continuous shedding of dust and gas is not just a spectacle, it's a testament to the comet's role in redistributing material across the solar system. As we delve deeper into these mechanisms, we begin to understand not just the comet's dynamics, but also its profound influence on the solar system's evolution. These hidden layers, like the rings of a tree trunk, reveal that the comet is not a homogeneous ball of ice and rock, but a porous body with varying densities and cavities. Rosetta's MUPA's instrument, a multi-layer subsurface penetrometer, drilled into the comet's surface, providing the first detailed look at its interior structure. The data revealed a surprising degree of heterogeneity, areas where the density differed significantly from one another. Scientists believe these density variations could be due to the comet's formation in the early solar system, when different materials were deposited and compacted at varying rates. As we gaze into the heart of this primitive celestial body, it becomes clear that comets like 67P are not merely leftovers, but critical pieces in understanding how our solar system coalesced. These hidden layers speak volumes about the comet's origins and the conditions that shaped it, offering a glimpse into the early solar system as it was taking form. And with every new discovery, we edge closer to unraveling the mysteries of these icy messengers from our past. Gravity and rotation are the key players in this cosmic drama, subtly shaping the comet's behavior over time. The interplay between these lobes is akin to a delicate ballet, where every shift and adjustment has profound implications. Imagine the neck between these lobes as a fragile bridge susceptible to these gravitational stresses. Over time, the constant pull can cause cracks and fissures to form, further weakening the bridge that holds the comet together. But gravity's influence doesn't stop at just creating fractures. These fissures can become pathways for the comet's inner ice and dust to escape into space, forming jets of material that create the comet's iconic tail. Thus, gravity not only shapes the comet's internal structure, but also drives its most visible and spectacular features. It's a remarkable demonstration of how even in these icy, remote bodies, forces we're familiar with can have such profound effects. And as the Rosetta mission continues to shed light on this enigmatic celestial body, we're reminded of how intricately connected our cosmic neighbors are, with forces that govern both them and us. These pits are not mere depressions. They hint at the comet's turbulent past, each one a record of a volatile outburst that carved into its surface. Cliffs as high as buildings stretch across its uneven landscape, their steep slopes defying the low-gravity environment of the comet. Amidst these towering formations lie boulders, some as large as cars, strewn around like giants' playthings. Their presence is a testament to the comet's active surface processes. Understanding these unique features offers insights into the comet's geological history, a timeline marked by eons of activity and change. As we continue to explore this enigmatic cosmic body, each new detail adds another layer to our knowledge of these icy wanderers and their critical role in shaping the universe around us. Carbonaceous matter-complex organic compounds, primarily composed of carbon and hydrogen, has long been considered a vital component in the study of comets. These compounds are believed to have played a crucial role in the early formation of our solar system and could potentially hold clues about the origins of life itself. The Rosetta mission, equipped with advanced instruments such as the OSIRIS camera and the MUPIS penetrometer, was uniquely positioned to detect these elusive organic compounds. By analyzing the data sent back by these instruments, scientists were able to identify a variety of organic compounds on the comet's surface. This groundbreaking discovery has significant implications for the field of astrobiology, which seeks to understand the origins and distribution of life in the universe. The presence of these complex organics suggests that the conditions present in the early solar system may have been more conducive to the development of life than previously thought. Furthermore, these organic compounds could serve as precursors to the building blocks of life as we know it, offering a tantalizing glimpse into how life might have emerged from the primordial soup. The comet's surface is not uniform. Instead, it is composed of distinct geological layers, each revealing a unique chapter in its history. These layers are the result of various accretion events that occurred billions of years ago during the formation of our solar system. By studying these layers, scientists can piece together a timeline of events that shaped the early formation of the solar system. One particularly intriguing layer is the building blocks of life's stratum, which contains organic compounds that could have served as precursors to the origin of life. Each layer tells a story, a chapter in the cosmic history that has been patiently waiting to be deciphered by humanity's curious minds. As we continue to unravel these mysteries, our understanding of comets and their role in the grand cosmic narrative grows richer and more profound. And, with each new discovery, we inch closer to solving the puzzle of our own origins in this vast and wondrous universe. Imagine standing on the surface of this ancient cosmic body. You might see plumes of gas and debris shooting into space, carving intricate shapes into the landscape. Scientists note that these jets aren't random occurrences. They follow a specific cycle driven by the comet's rotation and the sun's heat. Over time, these periodic bursts sculpt the comet's surface, creating cliffs, pits, and other distinctive features. The Rosetta mission reveals that these surface transformations aren't merely aesthetic changes. They play a crucial role in the comet's long-term evolution. Think of it like this. As a young child grows and develops, their appearance changes due to the processes happening within. Similarly, Comet 67P Churyumov-Gerasimenko's exterior alters as a result of its internal activity cycles. Understanding these processes enhances our knowledge of how comets evolve over millions of years, providing insights into the early solar system. And with each new discovery about these jets and their effects on Comet 67P Churyumov-Gerasimenko's surface features, we inch closer to unraveling the mysteries of our cosmic origins. Its internal structure is not uniform, with variations in density caused by differences in composition and porosity. Seismic data from the Rosetta mission has helped scientists infer the presence of large cavities beneath the comet's surface, contributing to its porous nature. These internal cavities are thought to be remnants from the early formation period of the solar system, offering insights into our cosmic past. This asymmetry impacts the comet's dynamics and stability, influencing how it responds to forces like solar wind and gravitational tug from larger bodies. Understanding these internal structures is crucial for deciphering the story of our cosmic origins, as they provide clues about the conditions and processes during the early formation of our solar system. Its complex structure, with two distinct lobes connected by a narrow neck, hints at the dynamic processes that shaped it over time. These components are not merely remnants. They play a crucial role in shaping theories about the solar system's evolution. Water vapor jets and dust plumes like those seen erupting from the South Pole fractures are key players. They serve as messengers from the past, carrying the potential to deliver water and organic compounds to young planets. Understanding this impact can refine theories about planetary formation during the early stages of our solar system's history. The Rosetta mission, with its detailed observations and data collection, has brought us closer to unraveling these cosmic mysteries. As we continue to decipher these internal structures, we deepen our understanding of Comet's significance in shaping our cosmic origins. The quantities of these organic compounds are not insignificant. The Rosetta mission detected enough methanol on the comet to fill several Olympic-sized swimming pools. These discoveries have profound implications for our understanding of life's origins. The presence of such compounds suggests that comets may have played a role in delivering prebiotic materials to early Earth. Imagine, if you will, the vast cosmic ocean from which these building blocks of life might have been delivered. As we delve deeper into the chemical makeup of comets like 67P, we gain new insights into the prebiotic Earth. This knowledge helps us piece together the story of how life might have emerged from the primordial soup. The Rosetta mission's groundbreaking discoveries contribute to the field of astrobiology, highlighting how cometary organic chemistry can inform our understanding of life on Earth. By illuminating the pathways through which these fundamental building blocks might have been delivered, we deepen our appreciation for the cosmic dance that led to life as we know it. Gravity, the very force that pulls us to Earth, also exerts its influence on Comet 67P Churyumov-Gerasimenko. The mission, reveal the complex internal structure within the comet, shaped by gravitational forces acting on its varied terrain. Comet 67P Churyumov-Gerasimenko consists of smooth plains and rugged cliffs that create distinct lobes, each with its own characteristics. Gravity plays a crucial role in this configuration, causing the comet to rotate on its axis every 12 hours. This rotation creates a day-night cycle for the comet, with sunlight reaching different parts of its surface at varying times. The differences in illumination across these lobes impact how they erode over time. Exposed to prolonged sunlight, the head or larger lobe tends to erode more rapidly compared to the bodies, which receives less direct light. This uneven erosion contributes to the comet's evolutionary changes, shaping its surface features over millions of years. Understanding this interplay between gravity and the comet's structure enhances our appreciation for the complex dance that shapes celestial bodies over vast stretches of time. These geological layers are like the rings of a tree trunk, each layer representing a different epoch in the comet's life. Each layer holds clues about the conditions present during its formation, offering insights into the early solar system. The formation processes that created these layers involved complex interactions between gas and dust particles, shaped by the gravitational forces of early celestial bodies. Over time, these particles accreted to form the comet's nucleus. Think of it this way: each layer of the comet is like a page in a cosmic history book, chronicling events that shaped our solar system and perhaps even life itself. By exploring the groundbreaking discoveries made by the Rosetta mission, we gain deeper insights into the comet's geological history and its role in shaping our solar system. And with each new layer uncovered, we get a step closer to understanding the cosmic forces that have sculpted our universe since its very beginnings. One of the most striking discoveries was the presence of a multitude of organic compounds, including amino acids and other complex molecules. These organic chemicals are the building blocks of life as we know it. Their discovery hinted at a possible connection between comets and the origins of life on Earth. This delivery could have provided the necessary ingredients for life to begin and evolve on our planet. Each layer of ice and dust, every organic compound, whispers tales of a time when our solar system was young and volatile. And with each new discovery, the story of our universe unfolds, one fascinating page at a time. These are the organic chemistry breakthroughs that redefine our place in the cosmos. The comet's surface was found to be rich in silicates and carbonates, which are common minerals on Earth and other rocky planets. These findings suggest that the comet might have formed in a region where similar mineral-rich materials were abundant. The presence of these minerals provides valuable insights into the early conditions of our solar system. By understanding the mineral composition of Comet 67P Churyumov-Gerasimenko, scientists can better piece together the puzzle of how our solar system evolved. This knowledge not only enhances our understanding of comets, but also sheds light on the larger cosmic story of planetary formation. This porosity affects the comet's strength and stability in significant ways. The cavities within its structure make it less dense than a solid ice body. The porosity of Comet 67P Churyumov-Gerasimenko contributes to its unique behavior when it approaches the Sun. As heat from the Sun penetrates the comet's surface, the water vapor and dust that are released create the spectacular tails we see. Understanding these physical properties offers a deeper insight into comets as objects that can provide valuable clues about the early formation of our solar system. Water vapor and carbon dioxide are among the key volatiles detected by Rosetta. These substances play a critical role in shaping atmospheres, as seen in other comets. The presence of these volatile materials indicates that Comet 67P Churyumov-Gerasimenko has retained a significant portion of the original building blocks from the solar system's early days. This composition suggests it is a remnant from the cloud of gas and dust that formed our planetary neighbors. Scientists believe that comets like 67P played a vital role in delivering water to Earth during its early stages of development. The comet's volatile content may have contributed significantly to the formation of our planet's atmosphere. By studying this volatile content, we gain a deeper understanding of how comets shaped the atmospheric conditions on early Earth. It's like unlocking a piece of our planetary history that was once hidden in the depths of space. The findings from Rosetta thus illuminate how comets contributed to making Earth habitable by delivering these essential volatiles. It's a testament to the profound connection between our planet and the distant objects that traverse our solar system. This knowledge deepens our appreciation for comets as not just celestial wanderers, but as vital actors in the grand narrative of solar system evolution. Their volatile content holds the secrets to our planetary heritage. At the heart of Comet 67P Churyumov-Gerasimenko lies a story written in ice and dust, revealing its ancient past. The mission revealed that these layers are not just horizontal, but also vertical, creating a complex geological timeline. Scientists found that the younger layers are rich in ice, while the older ones contain more dust and rocky materials. This stratification hints at changes in composition over time, shaped by the comet's formation processes. These findings paint a vivid picture of our cosmic ancestors, offering insights into the nascent stages of our solar system. Scientists found that the comet harbors a rich array of complex organic molecules, the building blocks of life as we know it. These compounds include amino acids, which are the fundamental components of proteins, and nucleobases, the bases that make up DNA and RNA. Their presence on a comet suggests that these molecules may have originated in space, potentially delivered to early Earth by similar cosmic bodies. This discovery challenges the conventional notion that life began solely from Earth-based processes and hints at a more interconnected universe. Imagine if these molecules, floating through the cosmos, played a crucial role in kickstarting life on our planet, a cosmic seeding of Earth's biosphere. The Rosetta mission thus illuminates the potential contributions of comets to the prebiotic chemistry of the early Earth, offering a glimpse into our cosmic origins. To explore these reservoirs, researchers used radar to map the comet's interior. The results revealed a complex network of subsurface cavities and water ice deposits. These reservoirs are crucial as they play a significant role in driving the comet's activity. When the comet approaches the sun, the water ice sublimates, creating outbursts of gas and dust. Imagine a frozen lake beneath a thin layer of soil. As the comet warms up, this frozen lake begins to melt, releasing water vapor that escapes into space. The presence of these subsurface reservoirs sheds light on the internal mechanisms driving cometary outbursts. They are not merely passive bodies, but dynamic entities shaped by their icy interiors. Moreover, understanding these reservoirs offers insights into the origins and evolution of comets in our solar system. They are time capsules, containing clues to the early solar system's composition. As Rosetta continues its mission, each new discovery reveals more about these icy wonders and their role in shaping our cosmic neighborhood. This understanding provides a window into the prebiotic chemistry that could have played a part in the birth of life on Earth, deepening our connection to the cosmos. Comet 67P Churyumov-Gerasimenko's journey through the solar system is shaped by unseen forces, including a magnetic field that scientists had not anticipated. This discovery has revolutionized our understanding of cometary processes and their influence on the early solar system. The comet's magnetic field is not generated by its rotation or internal dynamo effect like Earth's. Instead, it originates from the solar wind and its interaction with the coma, the cloud of gas and dust that envelops the comet. This magnetic influence is subtle but significant. It affects the comet's dust emission patterns, guiding the streams of dust and particles away from certain areas. In particular, The magnetic field shapes the jets of water vapor and dust that emanate from specific regions on the comet's surface. These jets are crucial for driving the comet's overall structure and appearance, as they carve out features like cliffs and pits over time. This insight deepens our appreciation for the unseen forces that sculpt the behavior and evolution of comets in the solar system. This understanding provides a deeper connection to the cosmos, reminding us that there is always more to explore in the vast and intricate dance of our solar system. As we continue to gaze into the cosmos, we find that the most profound discoveries are often hidden beneath the surface, waiting for us to uncover their secrets. This discovery has set new standards for cometary research, influencing subsequent missions to explore the complex structures and internal dynamics of other comets. These insights pave the way for future missions to uncover even more secrets about our cosmic neighbors and their role in shaping our solar system. Thus, the Rosetta mission's impact extends beyond its initial findings, setting a new benchmark for comet exploration and fostering an enduring legacy in our quest to understand the early solar system. Deep within the nucleus of Comet 67P Churyumov-Gerasimenko, layers upon layers of history are etched like rings on a tree trunk. Each layer tells a story, revealing insights into the comet's geological evolution over billions of years. The innermost core of the comet is primordial ice, formed during the early stages of the solar system's birth. This ice has remained frozen for over 4 billion years, preserving crucial clues about the conditions that prevailed when our cosmic neighborhood was taking shape. Surrounding this ancient core is a layer of water ice and dust, deposited during the comet's early formation phases. This material, known as interstellar grit, was forged in the furnace of dying stars, and it provides vital information about the chemical composition of the young solar system. One of the most intriguing layers is a thin film, rich in carbon-based materials, which could have been formed by exposure to cosmic rays or the solar wind over millions of years. This layer offers insights into how comets interact with their environment and evolve over time. These geological layers are not just remnants of the past, they are active players in the comet's current behavior. As the comet approaches the sun, these layers heat up and release gases and dust that form the comet's spectacular tail. In exploring these layers, scientists are not just looking back at the past, they're seeking clues to unravel the mysteries of our cosmic origins and the potential for life elsewhere in the universe. Each layer holds secrets that can only be unlocked through continued study and exploration. It's a testament to how much more there is to learn about these celestial wanderers. Methylamine, a simple organic molecule consisting of 1 carbon atom, 4 hydrogen atoms, and 1 nitrogen atom, is particularly significant because it can act as a building block for more complex biochemical structures. Scientists believe that these organic compounds might have been delivered to early Earth by comets and meteorites, contributing to the chemical soup necessary for life's emergence. The presence of these compounds in the comet suggests that similar conditions may have existed elsewhere in the early solar system, providing a window into the prebiotic environment that could have supported the formation of life's building blocks. These discoveries not only deepen our understanding of comet composition, but also shed light on the broader question of how life might have emerged from the primordial soup of prebiotic chemistry. By unraveling the story of these organic compounds, we gain a sense of how comets, with their complex structures and unique properties, have contributed to the intricate tapestry of our cosmic origins. Ultimately, these findings underscore the importance of continuing to explore and study comets, as they hold secrets that can illuminate the very building blocks of life. Each layer of discovery peels back another piece of the puzzle, reminding us that there is so much more to learn about these cosmic wanderers. Comet 67P Churyumov-Gerasimenko, nicknamed Rosetta's Comet, is not a static celestial body, but rather an active and ever-changing one. Its surface texture dynamics are driven by various factors that continuously sculpt its appearance over time. Sublimation, The process where ice transitions directly into vapor without melting plays a significant role in shaping the comet's surface. As sunlight reaches the ice deposits on the comet's surface, it causes them to evaporate, leaving behind patches of dust and debris that are gradually eroded away. Erosion also contributes to these dynamics. Small particles ejected from the comet's surface due to sublimation or other processes can collide with and wear down the surrounding material, further altering its texture and topography. Over time, these processes create a complex interplay of cliffs and pits across the comet's surface. The rugged terrain not only adds to its unique appearance, but also influences how jets of water vapor and dust are released from the interior of the comet. Studies by the Rosetta mission reveal that the activity of 67P is not just a relic of its formation, but an ongoing process shaped by these dynamic surface changes. This active nature of comets like 67P underscores their role in shaping the evolution and composition of our solar system. Though we often imagine celestial bodies as frozen in time, the truth is that they are continually evolving through a myriad of processes. The surface texture dynamics of Comet 67P Churyumov-Gerasimenko serve as a stark reminder of this cosmic waltz where each step reveals another layer of complexity and wonder. The dance of sublimation and erosion not only shapes 67P's surface, but also contributes to its unique identity in the cosmic family tree, reminding us that each celestial body has a story to tell about our shared origins. Detailed studies by Rosetta's scientific instruments unveiled that gas and dust jets play a significant role in reshaping the comet's surface. These jets erupt from the comet's nucleus, driven by sublimation processes where ice directly transitions into gas. As these jets escape into space, they carry away not only water vapor, but also tiny dust particles, effectively sandblasting the comet's surface. Sublimation is a process where ice converts directly into gas without passing through an intermediate liquid state. This constant erosion from the inside out creates unique surface features, such as pits and cliffs. Over time, these features evolve and change, providing insights into the comet's internal dynamics. Additionally, micro-impacts from cosmic dust particles contribute to the comet's erosion. These tiny impacts gradually wear down the surface over millions of years. These internal processes, which include gas and dust jet effects, as well as sublimation and micro-impacts, collectively shape the comet's surface over time. The data gathered by Rosetta revealed that the dust layers on Comet 67P act as a natural insulator. This insulation helps to regulate the comet's internal temperature, keeping it stable amidst varying solar influences. However, the thermal conductivity of these dust layers varies greatly across different parts of the comet. Some regions are more efficient at transferring heat than others. These variations in thermal conductivity play a significant role in how heat is distributed throughout the comet's nucleus. This uneven distribution can lead to different rates of sublimation and activity across its surface. Scientists found that the comet's interior is quite porous, filled with cavities that can trap heat and slow down its dissipation. This internal thermal management significantly impacts the comet's overall behavior. As Rosetta continued to study Comet 67P, it became clear that understanding these thermal properties is key to unraveling the mysteries of comets and their role in the early solar system. With each new discovery, our grasp on how these celestial bodies function deepens. The Rosetta mission brought us one step closer to deciphering the language of comets. Ultimately, these insights into Comet 67P Churyumov-Gerasimenko's thermal properties illuminate how internal heat management affects its behavior and activity. This understanding helps us piece together the larger puzzle of comets' role in the formation and evolution of our solar system. Scientists discovered that the comet harbors a variety of ice structures, each playing a crucial role in its evolution and activity. One key finding is the presence of crystalline ice. Unlike amorphous ice, which lacks any organized structure, crystalline ice has a highly ordered molecular arrangement. This difference is significant because the formation and behavior of these ice types can vary greatly under different conditions. For example, studies show that amorphous ice forms more readily in low-temperature environments, while crystalline ice tends to dominate where heat is present. The Rosetta data revealed that the comet's surface consists of a complex mixture of dust and various forms of ice, including crystalline ice. Understanding these mixtures is essential because they influence how the comet's surface responds to solar radiation and other external stimuli. The comet's porous interior, filled with cavities and hollow spaces, is what makes it truly unique. Research on the comet's pore size distribution showed that these pores range from microscopic to massive openings. Understanding the comet's porosity helps explain why it displays such intense activity during close approaches to the Sun. As the comet warms, gas trapped in its pores escapes, creating those distinctive tails and jets of dust we see from Earth. Imagine tiny geysers erupting all across the comet's surface as it draws closer to the Sun. This internal structure, full of nooks and crannies, is what facilitates the comet's remarkable displays of activity. Comets are often thought of as frozen remnants from the early days of our solar system. This internal heat impacts the comet's activity and evolution in profound ways. Imagine the comet as a giant block of ice in space, warmed from within. The findings have profound implications for our knowledge of conditions during the dawn of the solar system. These subsurface water ice reservoirs are critical for understanding how comets retain their volatiles over billions of years. They offer a glimpse into the environment that prevailed when the solar system was still young. Imagine a world where temperatures were so low that even ice could be preserved for eons. This is the reality we're peering into through our exploration of Comet 67P Churyumov-Gerasimenko. Scientists believe that these subsurface water ice reservoirs were formed during the early stages of the solar system's history, when temperatures were low enough for water to remain frozen. These findings enhance our understanding of cometary water distribution and highlight the significance of studying these celestial bodies. Ultimately, this knowledge helps us appreciate the vastness and complexity of the cosmos we inhabit. Among these organic compounds are amino acids, the building blocks of proteins, and nucleobases, which form the basis of DNA and RNA. These discoveries are significant because they shed light on the early formation of the solar system. It illuminates the comet's role in delivering organics that may have laid the foundations for life on our planet. But the most significant discovery was the presence of phosphorus, containing compounds which are essential for life as we know it. These prebiotic compounds hint at a possible link between comets and the chemical building blocks that could have contributed to the origins of life on Earth. Imagine tiny particles of these organic molecules raining down onto a young, primordial Earth, potentially providing some of the basic ingredients needed for life to emerge. While Rosetta's mission ended with a controlled impact into the comet, its legacy continues to deepen our understanding of these ancient, icy wanderers and their role in shaping our cosmic history. The more we learn about the chemical compositions of comets like 67P, the closer we come to unraveling the mysteries of our solar system's past and perhaps even the origins of life itself. And so, as Rosetta's final data is analyzed, each new discovery serves as a gentle reminder that we are part of something vast and wondrous, a universe filled with secrets waiting to be revealed. The release of these volatiles is driven by various mechanisms, including the heating of the comet's surface as it approaches the Sun. This process, known as outgassing, creates the iconic tails and comas that make comets such a spectacle in our night sky. Understanding how these different volatiles interact and influence each other is crucial for comprehending cometary behavior and the role of comets in the early solar system's evolution. As we continue to analyze Rosetta's data, it becomes clear that volatile content plays a pivotal role in driving the activity and behavior of comets. This insight provides valuable clues into the solar system's past and its ongoing dynamics. So, as we delve deeper into the secrets of Comet 67P Churyumov-Gerasimenko, we gain a profound appreciation for the intricate dance of volatiles that makes these celestial bodies such dynamic and fascinating inhabitants of our solar system. And as Rosetta's mission comes to a close, each discovery serves as a gentle reminder that the universe is filled with wonders waiting to be revealed, a testament to the power of scientific exploration and our shared connection to the cosmos. This discovery was puzzling because comets are typically too small and lacking in significant metallic content to generate their own magnetic fields. Researchers suggested that the comet's magnetic field could be a remnant from when it first formed, or perhaps even from earlier in its journey. Investigating this further, scientists theorize that the magnetic field might have originated from the early solar system's conditions or preserved from interactions with other celestial bodies. This revelation offers a unique window into the comet's evolutionary history, providing insights into the conditions present during its formation. Moreover, understanding this magnetic field could uncover clues about how comets contribute to the overall composition and dynamics of the early solar system. The Rosetta mission thus deepens our knowledge of these ancient cosmic objects, enriching our understanding of the vast and complex universe we inhabit. The Rosetta mission deepened our understanding of comets, revealing that these ancient cosmic objects are far more complex than previously thought. But what drives this complex comet's activity? It turns out that internal heat sources play a significant role. Scientists believe that subsurface heat is generated through mechanisms such as radioactive decay, similar to how the Earth retains its inner heat. These internal heat sources cause water vapor and dust jets to erupt from fractures in the comet's surface, creating the iconic plumes we see during its active phases. By understanding the energy dynamics within this comet, we gain a deeper appreciation for its role in the early formation of our solar system. And as Rosetta continues to send back data from its historic mission, it draws us closer to unraveling the mysteries of these enigmatic celestial bodies. Different regions on the comet exhibit unique chemical signatures, influenced by factors such as solar wind exposure and geological activity. Conversely, regions exposed to the harsh solar wind exhibit signs of significant erosion, with a higher proportion of dust and rocky material. Moreover, the presence of organic compounds on the comet's surface hints at the possibility that similar materials may have been delivered to early Earth by comets and contributed to the emergence of life. The intricate dance between solar wind exposure and geological activity on Comet 67P Churyumov-Gerasimenko showcases the dynamic nature of these celestial bodies, further deepening our appreciation for their complexity and significance. And as we delve deeper into the data, the surface composition variations on Comet 67P Churyumov-Gerasimenko reveal a story of resilience and evolution that spans billions of years. The mission employed state-of-the-art high-resolution imaging to capture every detail of the comet's surface. This advanced technology allowed scientists to create meticulous 3D models, bringing the comet's complex structure into vivid focus. But it wasn't just about high-resolution imaging. The stereo camera techniques played an equally crucial role. By using two cameras positioned at slightly different angles, scientists could map the comet's surface with depth and accuracy. These stereo images allowed for a three-dimensional reconstruction of the comet's landscape, providing invaluable insights into its topography. Features like cliffs and pits became tangible, as if one were standing on the surface of the comet itself. Illuminating the mission's innovative approach, these methods not only revealed the comet's intricate surface features, but also hinted at its profound history. The data gathered pointed towards a past shaped by cosmic interactions and billions of years of solar system dynamics. As the mission continued, each new discovery brought us closer to unraveling the mysteries of this enigmatic celestial body. The technological ingenuity showcased by Rosetta stands as a testament to human curiosity and our relentless pursuit of understanding the cosmos. The layered structures within Comet 67P Churyumov-Gerasimenko offer a glimpse into the geological history of this ancient celestial body. As Rosetta probed deeper, it uncovered intricate layers that tell a story spanning billions of years. Imagine if you could see a cross-section of the comet's nucleus, a complex interplay of light and dark, smooth and rugged terrains. These layers are not just remnants of its past, but clues to the early formation of our solar system. Scientists liken these layers to geological strata on Earth, each holding secrets about the comet's history and evolution. The outermost layer, for example, is a relatively new addition, a result of recent activity as the comet approaches the Sun. As we delve deeper, we encounter layers that are millions, if not billions, of years old. Each layer is a snapshot in time, frozen in place by the comet's slow rotation and the steady influence of gravity. The most inner layers, closest to the comet's core, are the oldest, untouched by external influences for eons. They provide a direct window into the conditions of the early solar system when this comet was first formed. Think of each layer as a chapter in the comet's life story. Each chapter reveals crucial details about the environmental conditions and cosmic events that have shaped it over time. By unlocking these secrets, Rosetta has offered us a deeper understanding of not just this comet, but of the vast and wondrous history of our solar system. This unique cometary geology is characterized by distinct layers, a testament to the intricate processes that shaped it. These layers contain secrets of the comet's formation and evolution, providing insight into how our solar system took shape in its earliest days. As Rosetta delved deeper into the comet's layers, it discovered organic compounds, the building blocks of life, hidden within its frozen depths. These compounds hint at the possibility that comets could have seeded Earth with the fundamental ingredients necessary for life to emerge. Each layer tells a story. Each discovery adds to the tapestry of our cosmic origins. Scientists identified various types of terrain on the comet's surface, including smooth plains and rugged cliffs. These different surfaces are believed to have formed at distinct stages in the comet's evolution. The smooth plains are thought to have emerged early in the comet's life, reflecting initial conditions during its formation. In contrast, the rugged cliffs are indicative of later geological processes that reshaped the comet over time. Rosetta's findings have inspired new missions and research projects aimed at exploring other comets and understanding their role in the solar system's history. For example, the European Space Agency's Comet Interceptor mission aims to study a long-period comet from the Oort cloud, building on Rosetta's success. This new generation of missions is crucial for unraveling the mysteries of how our solar system was formed and what conditions were like during its early stages. Understanding comets gives us a window into the past, helping to piece together the story of our solar system's genesis. The practical significance of Rosetta's discoveries cannot be overstated. They drive further scientific exploration and a deeper understanding of the cosmos. As we continue to explore, each new discovery builds upon those that came before, pushing the boundaries of our knowledge ever further into the vast expanse of space. The comet's interior is far from inert. It's a dynamic environment influenced by internal heat, which shapes the comet's behavior and structure. Thermal conductivity plays a crucial role in how heat is transferred within the comet. Efficient heat transfer within the comet can drive its activity, including outbursts of water vapor and dust. This internal heat also influences the comet's structure, creating distinct features like smooth plains and rugged cliffs. The implications of these findings are profound. They illuminate how internal heat shapes the comet's structure and activity. Using its suite of scientific instruments, Rosetta measured the comet's magnetic field, uncovering its strength and variations. The magnetic field is surprisingly strong and exhibits significant fluctuations as the comet approaches the Sun. These variations are not random, but are influenced by the solar wind, the stream of charged particles that flow from the Sun. This interaction can cause unexpected behaviors, such as the formation of plasma bubbles and the deflection of dust and gas jets. For instance, strong magnetic fields can repel charged particles, affecting how dust and gas are ejected from the comet's surface. The complex interactions between the comet's magnetic field and the solar wind offer valuable clues to the origins of our solar system and the conditions that governed its earliest days. Scientists found traces of minerals like olivine and carbonates that shouldn't typically exist in a comet's composition. These minerals are usually associated with asteroids, suggesting that the comet might have interacted with other bodies in its distant past. Moreover, the mission unveiled unexplored regions of the comet that had remained hidden from view. These newly discovered areas offered insights into the comet's internal heat sources, which play a crucial role in its activity. For instance, the South Pole region, known for its dramatic fractures and jets of water vapor, revealed a subsurface ocean. This discovery not only highlighted the comet's dynamic nature, but also provided clues about how water and other volatile materials were incorporated into it. These hidden gems advance our overall understanding of the comet's role in the early solar system and the conditions that governed its earliest days. Additionally, amino acids, the fundamental units of proteins, were found on the comet's surface. By studying these chemical compositions, scientists gain deeper insights into the materials that may have seeded life on Earth billions of years ago. Among the primary drivers of this internal warmth are radiogenic heating and residual primordial heat. Radiogenic heating is a result of the decay of radioactive elements within the comet's nucleus, while residual primordial heat harks back to the ancient formation of the solar system. These internal heat sources play a crucial role in shaping the comet's activity and evolution. They cause the ice within the comet to sublimate, leading to the formation of jets that expel dust and gas into space. This process is particularly notable near the South Pole, where fractures allow these heated materials to escape more easily. Scientists now hypothesize that similar ice-rich structures could be present in other comets, hinting at a broader distribution of these formations throughout the solar system. New methodologies for studying comets are emerging, inspired by Rosetta's groundbreaking techniques such as landing a probe and analyzing subsurface compositions. This shift in approach could lead to further exploration of similar cometary objects, pushing the boundaries of our understanding of these primordial remnants from the early solar system. The far-reaching significance of Rosetta's findings underscores the transformative impact it has had on cometary research, setting new standards for future studies. The Rosetta mission found amino acids such as glycine and methylamine, along with ethylamine, embedded within the comet's nucleus. The preservation of these compounds within the comet structure offers a unique window into the chemical environment that prevailed billions of years ago. Understanding the origins and significance of these organics deepens our knowledge of the building blocks present in the early solar system. This knowledge is crucial for grasping the potential role these compounds may have played in the emergence of life on Earth.